We all know that the limit of 1 plus 1 over n to the power of n approaches e, the base of natural logarithm, as n approaches infinity. But here I also want to show that not only it approaches e, but also as a sequence, it monotonically increasingly approaches e. And also this limit is also e. And I also want to show that this sequence monotonically decreasingly approaches e. Of course, here n is a positive integer. And we're going to use this lemma. We have n different or maybe equal positive reals. Then we have this geometric mean is less than or equal to the arithmetic mean. Alternatively, you can rewrite it as the following, as we get rid of the square root of the nth square root after we raise the power of n on both sides. And so here I'm gonna write the proof. So we want to prove this is a sequence. It is an increasing sequence. So I want to show that 1 plus 1 over n to the power of n, I'll denote it as bn, because we already used an here. But anyway, just the notation, is less than or equal to the next member of the sequence. Right? Does it replace n with n plus 1? So 1 plus 1 over n plus 1, quantity to the power of n plus 1. And that is denoted as bn plus 1. Right? So this is what we want to prove, right? An increasing sequence. So let me just rewrite this quantity into, so all I need to show is that, so this quantity, right, bn can be written as 1 times 1 plus 1 over n times itself, all the way up to 1 plus 1 over n. And how many of this quantity? I say there are n, many of them. So exactly n of this quantity. And including the 1, we have exactly n plus 1 candidates. So using our lemma, that is less than or equal to n plus 1 at the bottom. And 1 plus this, plus that, plus all the way to this. So 1 plus the same quantity. How many of them? N, many of them. So n times this quantity. So n times 1 plus 1 over n, quantity to the power of n plus 1. And this can be simplified down to, of course, here I have to stress that this is actually a strict inequality. Why is that? Because equal sign only holds true if all the candidates are equal to each other. But here it's not the case. For example, 1 cannot equal to this quantity because n is a positive integer. If n is equal to 1, then that becomes 2, right? So 1 does not equal to 2. And if n is larger than or equal to 2, then 1 plus 1 over n is simply a fraction, right? Fraction cannot equal to 1. So at least we have 2 candidates that are not equal. So here we have the strict inequality, right? So strictly less than that. So multiply everything out. So n times 1 plus n times 1 over so n plus 1. So here I have n plus 1 at the bottom. At the top I have 1 plus n plus 1. So n plus 1 plus 1. Quantity raised to the power of n plus 1. Now splitting n plus 1 and 1, I have quantity 1 plus 1 over n plus 1. Quantity power of n plus 1. And this is exactly bn plus 1. All right? So I've really shown that this is my Bn, right? Bn. I've really shown that Bn is strictly less than Bn plus 1. Right? So I've shown that. Right? So I can just get rid of the equal sign here. So here is a strict inequality. I've really shown that Bn as a sequence is strictly monotonically increasing. Right? So in other words, I've really shown the first statement is true. Right? This sequence is really monotonically, strictly, increasingly approaches E. And just clear up the board and then we will move on to the second one. Of course, first I have to show that this limit is also E, just quickly. So this quantity can be written as 1 plus 1 over n to the power of n plus 1. Can be written as 1 plus 1 over n to the power of n times 1 plus 1 over n, that is splitting the power into those two quantities. And as n approaches infinity, 1 over n approaches 0, and this whole quantity approaches 1. So this entire quantity easily approaches E as n approaches infinity, right? Because this is already known to be approaching E, so E times 1 simply approaches E. Okay, let's move on to the second statement. I want to show that as a sequence, 1 plus 1 over n to the power of n plus 1 is a strictly monotonically decreasing sequence. Let's just denote it as maybe Cn. Right? So decreasing, so that is larger than or equal to, I want to show that it is strict inequality, so larger than the next candidate, that is 1 plus 1 over n plus 1 to the power of n plus 2. That is after we replaced n with n plus 1. And this is, of course, denoted as C sub n plus 1. So we want to show that this Cn is a decreasing function. So again, let me just rewrite this one into something else. So 1 plus, but before I rewrite it, I want to stress that here we use this direction of the inequality, but here we have an opposite direction using this lemma. So therefore, I cannot straight away apply the lemma. I have to do some tweak. I have to maybe rewrite it as a reciprocal. Let's see what happens. What happens if I take the reciprocal? So 1 over Cn, so as long as I can show that the reciprocal is strictly less than the reciprocal of Cn plus 1, then I can, take the reciprocal again, so show that Cn is larger than that one, right? All I need to show is show this one. Can I show that? Let's look at 1 over Cn. What does that equal to? So 1 over Cn is equal to, take the reciprocal of this one. That is equivalent to taking the reciprocal of the inside, right? Then raised to the power of n plus 1, right? The same effect. So again, the inside can be written as n plus 1 over n. Take the reciprocal, becomes n over n plus 1. N over n plus 1. Then raised to the power of n plus 1. Right? Okay, so this time I can rewrite it likewise into 1 times n over n plus 1 times itself, all the way up to n over n plus 1. Again, how many of them do I have here? So I have exactly n plus 1 of them. So including the one here, I have n+2 candidates. And that is, of course, less than or equal to, of course, for the same reason, I have a strict inequality, because likewise, n1 can never be equal to n over n+1, whether n is equal to 1, 2, 3, all the way, it's obvious, right? So this strict inequality. So I have n+2 at the bottom, raised to the power of n+2. Right? At the top, I have the sum of those candidates, right? 1 plus this plus that. How many of those quantity? n+1. n+1 times this quantity, plus 1. So 1 plus n+1 bracket times n over n+1. I have this. And simply n+1, they can just cancel out. And this simply becomes quantity of n+2, n+2. So 1 plus n+1. And then I can just simply divide both the top and bottom by n+1. So now, top becomes 1, and the bottom becomes n+2 over n+1. Again, I can simply split n+2 into n+1 plus 1 and split up the fraction. And that is simply equal to, so 1 plus 1 over, so n+1 plus 1, split it up, becomes 1 plus 1 over n+1. 1 plus 1 over n+1, right? Let's just double check that. n+1, n+2, yeah, can be written like that. Quantity n to the power n+2. Then we can simply rewrite it into simply 1 over 1 plus 1 over n+1. Quantity to the power of n+2, right? That is after we distributed the power onto the top and bottom. And this looks like Cn+1, right? The bottom, right? 1 plus 1 over n+1 to the power n+2. This is actually 1 over Cn+1. And now I've really shown that 1 over Cn is really strictly less than 1 over Cn+1, right? 1 over Cn+1. Like I said, I've really shown that, right? Then I can take the reciprocal, change the direction. Then I have Cn is strictly larger than Cn+1. Right? Which means Cn as a sequence is really a strictly monotonically decreasing sequence. So that really I've shown that this quantity is really monotonically, strictly monotonically decreasingly approaches E. And in my next video, I will be using these results to prove some further interesting results.